Cześć, witam, dzień dobry. Niezmiernie jest mi miło wszystkich serdecznie tutaj powitać, zarówno studentów, jak i nie. Ja tylko szybko powiem, że przylecieliśmy dzisiaj z Londynu, jest nas 5. Ja nazywam się Kacper, tam jest Joshua, James, który dzisiaj jest dzisiejszym prelegentem, Marko, w środku siedzi Sayed, także jeżeli macie jakiekolwiek pytania na końcu, to jakiekolwiek szczegóły chcecie dogadać albo nawet pogadać o pogodzie, to nie czujcie się skrępowani. Wykład będzie o składaniu grafów wiedzy z metodami uczenia maszynowego. Przedstawi go James, który jest naszym Principal Scientist. Także proszę o brawo dla Jamesa.
What did he say? Good evening, everyone. I'm James. I'm doing some research at Grakn Labs. So the 5 of us have flown over today. We're actually coming here. Casper, you've just heard from, is going to talk at the Google Developer Conference tomorrow. So we wanted to try and make the most of our visit here. So we decided to have this talk. And wow, like great turnout. Thank you all for coming. So today. This is quite a deep dive into what we're working on at Grakn, and so I will try and lead you through what our thought process is, why we're doing what we're doing, and hopefully you'll take something out of where we think that artificial intelligence and machine learning is heading, although those are dangerous terms to use at the moment, they get kind of hyped up. And maybe you'll start to see some use cases for maybe your own work for what you're up to at the moment. Can I get a quick show of hands before I start? Who here is undergraduate? Postgraduate? Not a student? Cool, okay. I just want to know who you are, that's all. Okay, so the talk today is on Knowledge Graph Convolutional Networks. This is a term we made up. Right? So, like, if you Google it, you will only find what we've done, right, so far. So, what I'm going to do is I'm going to come around to why we think that this is a good idea, okay? So we're going to start off, let's see if this works. Yes, good. So, basically, we start from the premise that at the moment, in industry, the machines that people are building are not as smart as we would like them to be, right? Now, what's wrong with them? Well, at the moment, it's quite hard to build your machine learning models without meaning that they're very constrained to the domain that you want to be working in. So you can't transfer what you've built from domain A to domain B without an awful lot of work. They're reliant typically on big data. That's a really big problem. That means that some companies just don't have access to being able to kind of build the same tools that Google could build, right? With that volume of information comes a huge benefit in terms of creating this kind of tool. They often become really complex really quickly. They don't exploit the data that they actually have available to them. They often, most of the time, anyone who's here familiar with machine learning already, they know that you have a machine learning pipeline that just takes in tables of data. It's all flat. It doesn't tell you anything about, it doesn't look like the real world, the data that comes into it, right? So what we start doing is we start saying, okay, well, these are the problems we have at the moment. Why do we see them as problems? Well, we see them as problems because machines aren't performing on the same level as humans, right? They do some specialized tasks really well, but in general, we still see that we can't trust them fully, right? So, what is it that we have as humans that the machines don't at the moment, okay? Now, if we break down the human brain, this is rough, okay? If there's any neuroscience students in the audience, I'm sorry, it's not going to be good, okay? But this is the kind of rough capacity of what the human brain can do, and the various different centers that we have, that we know about in the brain, okay? Now, what we can see is that most of the time here, people talk about artificial intelligence, and that used to mean something really cool, right? That used to mean like general intelligence, the kind of thing that's, Terminator's gonna rise up and kill us all or something fun, right? But it doesn't really mean that anymore, right? Because people started doing machine learning, and then the marketing guys got hold of the term machine learning, and they're like, well, no, we don't just do machine learning, we do AI, right? right? So they upset it like this, but actually all they're doing is machine learning, because that's a subset of AI, right? So if we start from the idea, we're not worried about coming up with a general intelligence, we just want to make something smarter than what we have at the moment, right? So the general idea here is, well, what can we do what can we find within the skill set that we have that we can give our robots, right? And if we look across this skill set at the moment, what we see is there's a lot of these things that we don't want to give them. We don't really want to start giving them emotions at the moment, right? We don't need to give them a hearing or movement control. You know, most of the machines we're talking about, they're bots for on the web to help, or software bots, right? We don't need them, we don't need to replicate humans for these things to be useful to us, and you can argue that you shouldn't, right? So if we actually iron out this into a few key things that we want our machines to be able to do, we get reasoning, learning, and long-term memory. These are the three things that you can find on this map that you can find will be able to, you know, make your thesis go a lot faster for you, or finish some project for you, right? Something that's actually just going to be a tool that you can use, but one that you can actually depend upon, right? So what I'm going to want to do from here is I want to start digging down into those three things, tell you what we can do at the moment, what we can't do at the moment, and where we think that we're going to go. So let's start with learning. So learning is absolutely saturated at the moment with a multitude of different techniques that you can be using, okay, right? So we see support vector machines, we see Gaussian mixture models, we see k-nearest neighbors, linear regression, and obviously neural networks, the big hot topic at the moment, right? And yes, I'm victim to neural networks as well. So we see that this space is really full with ideas, okay? And we also see that the industry support behind those ideas is also massive. This is just some of the top frameworks that are around that people are using at the moment to build their tools, right? And so you can see immediately that this is a well-supported area. So is this really where we're going to actually find something that's going to take us on to the next level, right? No, Mark. Marco says no. No, it's not, right? So let's come back to where we were before and start talking about something else, right? So let's start talking about, where are we going? Reasoning, okay? So what is reasoning, okay? When I say reasoning, what I mean is this logical capacity that we have, right? So I think mostly, I picked a silly example here, and I'm going to spend too much time talking about this silly example, as you'll see, right? That I think we can all look at that picture and we know, like, probably what we want to do, right? Now, the thing is, if you give that to a machine, right, it's going to be pretty tricky to be like, well, you just put it there, right? It seems like it's kind of trivial, but it's quite tricky to teach them to do that. And when we actually start thinking about, well, if I was to try and do that, if I was trying to teach a machine how to do that, what tools do I actually have available to me at the moment? Like, what can I install on my computer that's going to help me? Is TensorFlow going to do that for me? So this is the closest thing that anyone knows about at the moment, which, so there's a few grins, right? Some people has this been forced upon you at some point? I don't know. It nods. Yeah. So I encountered it, right? As you go through uni, you go, what's the point? No. Right? That's the only thing you think of this tool, right? Not popular. Now, the reason now, we're not just winning a popularity contest here, right? That's not the aim, but there's clearly something wrong with this tool, which is because there's only one like it, right? And it's not helping people. People don't see the value. They can't see why they would want to use that, right? So let's get rid of that. So what we're doing when we use reasoning is we're actually applying this mental model of rules that we have. Now, here we're going to talk about like really strict rules, okay? So it's sort of like, yeah, you know, these things must be true, therefore this is true. So what we can do is we can define a rule, and we're going to try and solve the fit the last jigsaw piece in the whole problem, okay? Something I invented like this week, okay? So this is a new thing, right? We're going to try and make it a thing, right? So when something is true, then something else is true. This is the premise that we're going to try and work on with this, right? And this is what we do as humans all the time. We say, well, when I spill my coffee, the floor will become covered in coffee, right? It's trivial, like we think we do it all the time. But to teach the machine that is a different thing. So we could set up this kind of formalism where we say, well, when the piece has this edge shape, right, this particular edge shape, and the whole has this kind of edge shape, right, and those edges are opposite in direction, right? So if you imagine a little arrow, which I should add to the presentation, if you imagine a little arrow pointing out of the edge of the jigsaw piece, right, when you have an arrow pointing out of the whole jigsaw, which has a hole in the middle, that arrow points into the hole. So what we want to find is that if we have these mathematical edges, right, we want to find two edges that look the same but have an opposite direction. Okay, and if we find that, one edge belonging to a piece and one edge belonging to the whole, then we find that the jigsaw piece can fit in the hole, right? So this allows us to basically infer additional information on top of the information that we have already. That's what we're actually doing when we do this deductive reasoning, is we're saying, I already know that these two edges look the same and that one's the opposite of the other, therefore I know that the piece fits into the puzzle. Now the thing is that that is very important, right? Because that works on this micro scale when you've just got one extra fact that you're inferring from the information that you have. But it also works as you scale that, okay? So we just provided this much information, right? And that was all we provided. And from that, we gained this much information, okay? Now we didn't need to add anything else. We could just write down those three initial facts, right? And from those, we could get one more fact. So what we'd like to be able to do is get computers to do that for us, so that then they can compute more and more facts based on only a subset of data that's actually required in the middle, okay? So the idea here is that we can expand the amount of data that we actually have without actually adding any more data. All we have to add is this logical reasoning basis. Now this is particularly important because it already addresses one of the problems that I already talked about, which is in machine learning requiring big data. That is very, very common. Now, if instead we can have small data, right, but we can scale it up to be much bigger than it is originally, right, suddenly we can start to overcome that problem, and smaller companies can start to compete with the likes of Google because actually they can really retrieve the same value from their data where, in the same way that a human could, right? The same way that a human can look at a set of facts and draw all of the conclusions. At the moment, you have to feed like 10 gigabytes of data into a model to get somewhere with it. So that's the idea behind the reasoning, but how do we actually get machines to do the reasoning for us, right? That's the important step. How do we actually go from us being able to do it to teaching them? So what we have here is the idea of symbolic automation. So we can provide essentially a set of equations, right, to our machine and fill in some of the gaps for it, right, and let it do the rest. So what I'm going to try and do here, can you guys see that? Can anyone see it? Is it too small? Too small. Okay. Oh good, it's close. Ah, it's up there. Magic. Go. Jigsaw rule. Okay. Okay. So the general idea here is that we can take the. Oh, I can't see the whole thing. We can work it out, right? Yeah. Okay. Good. So the idea here is that what we can do is we can take the three pieces, the three facts that we had just now, we can actually write down some kind of formalism for those facts that lets a machine do the inference for us, right? So what we do here is we assign variables which have the $sign in front of them, right? So we start with the when. We start with, well, when do we infer this new knowledge? So we say when variable p is a jigsaw piece. Okay, so we assign the fact that p is a jigsaw piece. Okay, we don't know which one, but we're looking for a jigsaw piece and we're calling it p. Okay. Then we have a shape p, that's all one variable, forget the highlighting, it's all one variable, right? And that is what we call a relationship, is what we're defining there. So we have a relationship which relates an edge, right, and has a shape owner. Okay, and that shape owner is the jigsaw piece. So what we're saying is we've got this jigsaw piece, that jigsaw piece has an edge, and we're connecting the edge and the jigsaw piece by the fact that there's some sort of ownership between those two, right? Now, we also describe what the edge is and what it has. So we say that we define that the edge is a specific type, that's edge, and we say that it has a direction and some contour type. But so at the moment we're looking at that shape which has, you know, the four nodules coming out of the jigsaw piece, right? That's the type. That's the actual shape of the contour itself. And then what we do is we define that we're looking for a gap, and we assign a variable to that gap. Okay, and we assign basically everything the same except for the edge direction. So the edge direction, we specifically were looking for something which is running in the opposite direction. Okay. Now what this is essentially doing is what we're saying is we want to conduct a search over all of the pieces that I have in front of me and all of the holes that I have in my jigsaw, right? And I want to find which piece will fit in which hole, right? That's the idea here. And so what we say is when these conditions are all met, then we have a jigsaw piece fit, okay? So that's a piece, we're generating a new piece of data, which again is in this format, we call it a relationship, to say that we have a missing piece, which is this piece which fits in this particular gap, right? So with this formalism, with this kind of idea, it starts to become reasonable to think that we can put this into a computer and then it can generate that fact for us, right? And if we can do it for that, this is a totally general framework for how you could write these things. Okay, that means that you can write rules, okay, but you can write rule A to generate some fact, and now we can generate some other fact based on this fact, right? And we can keep going like that indefinitely, right? I think we can actually even say that the amount of extra information we can generate grows exponentially as we add the rules. So let's try and get. Oh, good. Yes. Okay. So we've been here. So what we find is that using that kind of method clearly requires us to have stored our data in some specific way that allows the computer to search over all of the edges, and it needs to know what an edge is, right? It needs to search all the gaps. It needs to know which pieces of information are gaps, right? It needs to make these connections. So we need some way of doing that storage, okay? Which brings me very neatly, I'm sure you'll agree, back to this diagram, right? So we've already touched on learning and we've just touched on reasoning. So now we're going to talk about long-term memory, right? So that sounds like the structured data store that I was just talking about, right? So if we move on, what we're going to find is that long-term memory, okay, in general, what it sounds like we're talking about there is a database, right? Now, the unfortunate among you will be thinking of things like MySQL, right? Where you might be thinking, if you're really, if you got a bit further, you might be thinking about a graph database, right? Something like this. But the thing is, what you end up with, if you're trying to get something close to what we have as humans, you end up with something that should be kind of more of a mess than that, right? It looks more, you can imagine that it looks more like this, right? Most of us, if you ask to describe how does my memory look, we don't actually think that it's a set of filing cabinets in the back of our head, right, that we can just go routing through on demand, right? We know that it looks more like this, and that we have to think really hard to find some pathway to get to the memory that we want, or trigger it somehow, or whatever, right? So we know that it's more like a network, okay? So the thing about a network like this, if we try and build this as a system for a computer to read, is that if it's just a jumble, how is the computer ever going to find anything? If it's got to comb through terabytes of data, right? So again, we're back to the fact that for this memory, we want to bring some structure in. So what we can do is we can define a structure, again, using this. Oh, we can see it this time? Yeah? It wasn't very emphatic. Can we see it at the back? Yes. Thumbs up. I like it. Okay, so I can't see it then. So here we see a similar kind of syntax to what we saw just now. Let me see, where's this slide going to take me? Okay, Shh, you didn't see that. Right, so what we're going to do, okay, is we're going to start by, we're going to use this, what we call a define statement to say, well, now we're going to actually start defining what the model looks like that we want to search, okay? So you've seen all of these things already. You've already seen all of these bits and pieces, right? This is just the definition that actually holds it all together, right? This is the formula that underpins the data that tells you how you can put your piece of data in, all right? If you try and insert a dog as a jigsaw piece, it will tell you no, right? That's the idea of this, right? It will tell you what makes logical sense and what does not, okay? So, but what we introduce here is we introduce a few extra keywords, which is entity, relationship, and attribute. And that's the structure of the model that we think is the direction that people should be pushed in. Because most of the things you can think of in life, to our knowledge, all of the things you can think of in life, you can put under one of these categories, right? With that kind of a model, you can basically, we think, express basically any kind of data structure. Right? So that's a powerful thing, because then it means that you can actually describe stuff to a computer, right, but that actually goes in reality. You should actually be able to translate your own experience and your own knowledge of some domain, whatever that might be, right, into a language that the computer can understand. So, you didn't see this, remember? So that way, what we can do is we know that it's then easy to search through this data, because we now know, now the computer knows, oh well, this piece of data is this type, this is this type, these are connected in this way, right? And so you can then move across a big database with relative ease compared to if you're moving across a big mess like we saw just now, right? And that means that it's possible to automate the reasoning that we saw just now, right? So, oh, we've talked about that already, okay. So this is the kind of search that I'm talking about, right? So here we would say we want to match for some particular things that we find in the database, right? So we're going to look for a jigsaw piece, right, which is the missing piece in a gap which has a jigsaw piece fit. So what we're saying is we're trying to look for some relationship that links a jigsaw piece and a gap in a jigsaw puzzle, right? And so when we ask that question, because of the reasoning that we already added to this system, right, because of the structure that we gave to the data, it's now going to feed us back with any matching pairs of a jigsaw piece and a gap that that jigsaw piece will fit into, right? So it should be able to solve those last pieces of the puzzle just automatically from that query there. So the idea then is that we order things a little bit more than we have in our own heads. So rather than having the kind of fuzzy picture that I showed you just now, which is just a mess of all sorts, instead you end up with something that looks somewhat more ordered. It can still be a massive web and be highly complicated, but there is actually structure sort of within the madness somewhere. That's the idea anyway. Okay, so we're coming on to the meat of the thing here. So what we're going to do is we're going to talk about how do we actually combine all three of these different fields. Okay, so the thinking here is that we have learning, reasoning, and long-term memory. That's the key areas that we've already talked about. And what we want to do is we want to build a learner to do the learning for us, a reasoner to do the reasoning for us. And then importantly, the long-term memory is perhaps the biggest shift, which strikes up images of hard drive data or something like that. Instead, what we want is what's called a knowledge graph. Okay, so that is essentially the kind of structure that I've already shown you. It distinguishes itself from all of the other data structures that you're going to come across in so much as that it has this underlying structure. That means that your data is queryable. We also talk about the fact that a knowledge graph, you've seen just a basic example so far, but you can have relationships pointing to relationships. You can have attributes of attributes, so a value can have a value. So I can give you the word tack, okay? I can attach to the word tack the fact that the language of that word is Polish. Okay, did I pronounce it right? You look, give me odd looks. Right? So you can basically, the idea being you can compound these things, right, to a point where you can express everything, and that is what we call a knowledge graph, right? Now, the general idea here is that what we want to do is we want to put the reasoner on top of the knowledge graph. You've already kind of seen an example of that, right? But what we actually want to do is we want to go the step further from that, right? Which is to also provide the learning on top of the reasoner, on top of the knowledge graph. Because if we can do that, then you can build a machine, right, that shouldn't like steal the email that you, like the email reply you just got from your professor after you just emailed him. You know, you do that, and then your spam filter just like steals it for no reason or something, you know? Like these, the kind of stupid inaccuracies that you get from machines at the moment, the reasons that we can't trust them, we're hoping that we can alleviate by combining all three, right? So that's the basic architecture that we are aiming to try and build, okay? So, what do we have here? What tools do we have? This is the big unveil, by the way, in case you didn't feel it coming, right? So what tools do we have that can help us to do this along the way? Well, what we have is we have Grakn. I told you it was coming, right? So we have Grakn, which gives us both the knowledge graph and the reasoner, okay? So the idea there is that what we're actually doing as a company is we're building some people call it a database. We prefer a knowledge graph, right? But what that does is that holds your data, right? It holds it in this graph format for you with this rich context to how your data, what type of data all of it is, right? And on top of that, it also provides the reasoner in a way that's all in one box, right? So whenever you make those queries that we saw just now, all you have to do is ask the one box, what's the answer, and you get the answer straight back, right? You don't have to build, you don't have to roll this yourself, you don't have to plug any components in together. You just supply facts to the database, right? And when you query for some question, if it has directly inferable answers, or the direct answer themselves from the data, it will just give you that straight back, right? Now, knowing that I'm pitching to quite a lot of students today, what this talk doesn't go into is how that's useful to you guys right now. And maybe this is a good point to actually interject with just a little bit of that as a slight side note, which is to say that whenever you're dealing with complex data and you need to be able to find paths through that data, this is a really good tool for it. Worth noting actually, particularly for students, that this is, we have a totally open source version which has all of the functionality available unless you need to work on a cluster, okay? So this is actually, what we see is that this is a really great tool for academia because you don't need to touch Excel anymore. No one likes it, no one wants to do it, it's a dirty word, right? No one wants to go there, no one wants to trawl through all of this data in this cumbersome way. So the idea here is you can load the data once, you can load it in whatever way you see fit, write a couple of rules if you need to, and then you can pull all of the data out in the format that you actually need it, right? So, what about the learner? So that's really the premise of this whole talk, is how we start from a position of knowing that we've already got Grakn, okay? Like we're cheating a little bit there, right? So what do we build on top of Grakn that's going to get us somewhere else, okay? And so that is Knowledge Graph Convolutional Networks, okay? And we're going to use TensorFlow for that. That's the plan, okay? So, what does that thing actually look like? What does it do for us? How do we try and architect this thing? So we've done a bit of head scratching on that point. And what we see is that we have a lot of people in a lot of different fields wanting to use Grakn. They want to use it for a lot of different purposes. But the problem that you have is, when I want to use normal machine learning techniques, the kind of run-of-the-mill stuff, your SVM, your linear regression, whether you want to build your own neural network, whatever it might be, you're now starting from a point, if you put your knowledge in a knowledge graph, where, well, how do I actually do learning over this graph? That's really difficult. How do I get my data into this kind of flat format that we're all used to? I don't know how to do that. So I can't actually get started doing machine learning until I know, or leverage the knowledge graph until I can kind of make this bridge, okay? So really, this work is an attempt to kind of bridge that gap. And that's what this slide is going to be about. So what we're going to start off with is some basic query to the knowledge graph, okay? So I don't know who's familiar with the iris dataset, but for whatever reason I just flipped over to that, right? I'm not going to use it much, it doesn't matter. So the general idea though is that you're going to ask some question of your database, right, which may be complex or it may not. In this case we picked something really, like I literally ran out of space on the slide, so it's got to be short, okay? So we start with this concept, with a set of concepts is what we want to generate from this, right? We want to get, I'll explain what a concept is. We're going to query Grakn for these answers, okay? For answers to our questions. So in this case I'm asking for flowers, okay? Don't do it that often, I'm going to ask for flowers. Right, so I ask for flowers, right, and basically the database is then going to spit me back all of the different facts that it holds that match that criteria, okay? So in this case it's going to give me back all flowers that are an iris, right? That's the type that we're looking for. So we've got some set of data now that we've managed to get from the database, and then what we want to do is we want to pass that on, okay? We want to say, well, okay, these concepts, what do they actually look like within the database? We want to find some representation of these flowers. That means that we can now pass that into our machine learning pipeline to identify exactly which species it is, for instance. Okay? So what we want is some representation of that that's flat. So what we do is we feed those concepts directly into the Knowledge Graph Convolutional Network. I'm just going to call it KGCN for now, okay? And that's actually going to also ask some questions back of the database. It's going to go back and forward a little bit, and we'll go into that in a bit more detail in a minute. And then the output of that should be this matrix. And this matrix for each row is going to be an embedding, what we would call an embedding, for a single one of those concepts. So an embedding is essentially just a vector representation of that concept. And what we want that to do is we want it to describe the surroundings of the concept itself, right? What part does it play in the wider graph? We want to know everything about it, because if I'm querying for people instead, if I'm looking at a social network and I want to analyze it, okay, I want to analyze you and I want to analyze you, right? I want to know what you're like, I want to know what your buying habits are like, I want to know who your friends are, or whatever, something horrible. Like, you know, companies want to do this stuff, right? And so that means that I need to understand what your local network looks like. And do you look like, okay, yeah, I know who your friends are, and I know all this local data about you, but I also want to know, how do you compare to that guy over there, or that guy over there, right? How do I start to compare these subgraphs that aren't actually connected to one another, but they look similar, okay? So that's what we want to try and capture in the simple format of however many numbers long in a sequence, right? So the idea here being that every one of these rows, okay, will pertain to one of the results of that initial query, whatever it is that you wanted to, the individuals that you wanted to find out about. Okay, so then the idea is that once we've got those, right, that is the typical input that you're looking for machine learning down the line. This is, for those of you who've worked in the domain, this is feature vectors, right? That's what we're talking about here. We're talking about a massive set of feature vectors. And ideally, we want to also be able to do this in a batch process, right? So we don't have to, you know, map all 1 billion Facebook users at one time, right? That kind of thing. So that's the starting premise for why, the motivation, if you like, for why we're doing this work, because we really want to be able, people to be able to get off the starting blocks, building their own machine learning models based on the knowledge graph. Okay. But as a side note, we do actually. By default, we'll be able to do things like classification tasks just using this work, because that's how we're going to optimize what we're doing. So we do get some immediate benefits out from using the KGCN straight off. So what we're actually doing here is we're taking some work that's pretty fresh out of Stanford as of last year, and we're adapting it fairly heavily to try and make it work over a knowledge graph. Right? So bear with me with this slide, okay? Because it gets a little bit heavy a little bit quickly. But I'm going to try my best. Okay, so we're going to start with one of those concepts of interest, right? One of the things that we want to examine, and we want to know roughly what it looks like in its sort of itself and what's around it. Okay, so the first thing we do is we ask Grakn a question. We say, okay, what is immediately next to this thing? Okay, what's it connected to directly? Okay, and we get some set of things. Okay. Now, we're going to ignore the dotted line for now, and we'll circle back around to it, okay? So these are the things that are direct neighbours of the thing of interest, okay? Let's call it the star, shall we? So we've got the star and we've got its direct neighbours, okay? Now, what we're actually going to do, because the star might have 10,000 direct neighbours, okay? And pretty soon, if we're starting to look at a lot of data, this is going to blow up. So we actually subsample this, so I'm just going to throw one away, right? So we subsample this totally randomly, and we actually tend to find that that's going to give a good representation of what something actually looks like, despite the fact we've thrown some information away. Right, now, what we're going to find is that there's information in general, okay, we're going to talk in general terms of stuff, there's going to be information contained about those neighbours. Right, so we know something about all of those neighbours, we might know what they look like, we might have some data attached to them, we might have a couple of different things we'll come on to, but we know we have some information about them, and we're going to assume that that's in the format of these kind of feature vectors, and we've denoted them as boring, like 3x1 vectors at the moment, okay? So let's assume we have that. Then what we want to do is we want to somehow bring together all of the representations of the nearby neighbours, okay? We want to bring all of them together to try and tell us something about what the star is, okay? So we've got this process called aggregation here. Now, this is slightly tricky, but what we're going to do is we're going to go into the detail on the next slide of how that actually works. But the idea is what we want to do is somehow compress that information that we have into one vector in the middle, okay? So that red vector in the middle there, that is representing somehow the sum, the aggregation, the accumulation of all of the data that's held in those nodes marked 1. Okay, so they're all the guys that we found, and we've got one step away from where we started. We grab all of that information, we somehow bring it in together to make some sum total, okay? So from there, what happened then? What happened? What do we see? Oh, that just disappeared. Okay. Okay. What's happened? There we go. Okay, I got it now. Right. So what we also have is we also know something about the star itself. Okay, so we also have information directly about the thing that we're talking about. So we don't want to leave that out because that's really important local information. It might just be your name or your age, right? This is all important stuff that we already leveraged with quite good results. We don't want to miss that out. So what we're also going to do is going to do some combination, okay, where we want to actually aggregate that information as well. So that we've got another magic black box process that's going on there. So we've got two magic processes that we want to sort of untangle as we go on there, okay? So the thing is, one direct neighbor may tell us something, but we don't know how much, okay? In the general case, we have no idea how local the information is. It's going to be, where's that information that's going to be helpful to decide what this thing is, what it looks like. Is it 1 hop away? Is it 7 hops away? We don't know. So we basically generalize this. Is that what's happening on the slide? Okay. Oh, no, it's not. Okay. So we generalize this. We'll come back in a second. So we generalize this to go out to those 0.2s. Okay. So we can go an extra hop further, and we can do that k times. Okay. So the only limit on that is how much processing we're willing to do on each of the things of interest, and also whether or not we actually still gain information. So actually, it seems like the limit tends to be reached actually a lot quicker than you would think. It depends on how dense your data is, but the indications are good that actually this is tenable, this is doable, this will actually give something useful. Right? So I'm going to jump back a second. So the dotted line was the bit I was supposed to explain before that bit. Right? The dotted line is to denote something that's been inferred. So Casper's grinning because this is his bit. This is the bit he builds, right? So we've already seen this from the jigsaw, right? Where this is the piece that we've found fits in the hole. Okay, we've inferred that the piece fits in the gap. Okay, so how do we infer that? Well, we infer that by any number of other connections that are in the graph that may link those two things. Okay, so we could have a rule, or a rule on a rule on a rule on a rule. We could have any number of those things, right? But if that defines that there's some connection that's just 1 hop away from where we started, right, then that will be picked up with that initial search. When we initially ask, find me all neighbors 1 hop away from this concept that I'm interested in, okay, it's going to find this one, It just does its detective work, it does its deduction, and it figures out what's nearby. Okay? And what that lets you do is that lets you include in this small neighborhood search really important information that's actually only logically distantly connected to the thing that you're actually interested in. Okay? So the idea there is that this can extend like way beyond what we're capable of being able to conceive. We think, oh, well, is this a factor? Is this a factor? Right? And instead it can do this deduction for you at great scale, bring all of those things in nice and close, the important things in nice and close to the thing you're interested in, and then we can look and see whether or not they actually have any importance. So if I jump back to here, so what we then do, we've gone now 2 hops away, right, and we're using reasoning at all stages that we move away from that central concept of interest, right? And so now what we need to do is we need to do the same process again that we started with, right? We need to do this aggregation and combination process to take the features from the second layer and bring them to the first layer, okay? So that's the general principle of this, and actually I've given this to you slightly backwards because that's where we start. So we start at the furthest reach that we're willing to go, whether that's 2 hops, 7 hops, 11 hops, whatever it is, right? And then we start with those features, and then we basically bounce our way in, accumulating information as we go. So that, for instance, this point here, okay, the vector that we started off earlier is a line. Okay, I told you a line. So we started with these vectors, okay, and then we aggregated those inwards to give this vector, okay? We aggregated and combined to give this vector. And then this was aggregated and combined with these guys to move into here. So we get this big recursive iterative process. And the idea is that hidden in all of that information, in all of those processes, okay, is information that we care about. Okay, so the idea is that process has touched everything that's within however many k hops of the thing we're interested in. Okay, it's touched all of those things, and it's brought all of that information in, the useful bits, that is, okay? And then we have some central representation, which is here, okay, which we know now has some relation to all of this stuff, okay? So that's the general ethos behind the work that we've been following, which is this aggregation and combination dual step, okay? So we're going to dive into exactly like demystify the aggregation process a little bit, and then the combination. Apologies if you all fall asleep, but I feel like it's like I've got to give a machine learning lecture and put some neural network in it somewhere, right? Like you'd be disappointed otherwise. So, but the general idea here is if we've got like 3x1 vectors, okay, and those are the representations that we've got from those 4 neighboring nodes, okay, what we're going to do is we're going to put them through the simplest neural net ever, is the idea, okay? We just put them through a 1-layer neural net, okay? And so we can't call this deep learning, I guess. So then the idea is we pass all of those 4 through individually, and then we get their corresponding outputs, okay, from this neural net, right? Once we've got that, what we're really trying to say when we do the aggregation, this aggregation step, is we're trying to say, okay, so I've got 4 neighbors. Each of them has some piece of information about themselves, right? I want to look up the pieces of information they have, each of them individually, come up with some sort of representation of them, but then also I don't want to favor neighbor 1 over neighbor 4 just because they happen to come out first in the list, okay? So we need to be agnostic about, we need to not care exactly which order these neighbors came in, otherwise we're going to just pick unfairly for no reason. So what we then have to do is we have to do some kind of pooling operation. So this is things like max or mean, okay? These very simple operations are agnostic of the order of the things you put in. If I give you a list of numbers and I ask you for the mean, right, you don't care what numbers those, what the list of numbers, the order of that list was, right? You just care, you just give me the mean, okay? So the idea there is we've now, that demystifies the magic of trying to get from 4 neighbors down to a representation, okay, that has some information about all of them. The idea is it kind of picks the best bits, right? It picks the best bits of all of them. So that's how the aggregation works. If we talk about the combination, so now we've taken the information from all of our 4 neighbors, okay, and we've got some representation that we think is gains some information for us about these neighbors. We then want to combine that with the information we have about ourselves. Okay, so we want to stack that on top. So if that's the information coming from the neighbors, that's the information about me, right? Then we're going to concatenate these two into one vector, right? And then we're just going to do dot product, for those of you paying attention in your linear algebra lectures, right? We're going to do the dot product, okay? And with a weights matrix, right? And that's going to give us some combined output. And we can choose, we can define how big we want that output to be by choosing how big we want this weights matrix to be. That's the general ethos here, right? So I'm gonna point out that some of these matrices, like between the different slides, they're different sizes. Don't go home and think that this is all correct and everything, right? It's not fully thought through. It's just right. So from there, right, what we can see is we've now managed to get, via these two steps, the aggregation and the combination, I've now got some vector that has information about my neighbors, compounded into one thing, and added to what I have about myself, okay? So, but obviously we haven't talked about training this yet, okay? So, I'm going to take you back to, let's go back to the simple version of the graph for a second. So I'm going to talk about the training phase just very briefly. So what we want to do there is we need to actually have some sort of objective that we're going to fulfill, right, when we're training that model. So what we're actually going to do is we're going to take that representation that I now have of myself, which is not only based on my neighbors, but based on my neighbors' neighbors and my neighbors' neighbors' neighbors, if I want it to be, right? And I've got that representation of myself, but now what I do is I just do some basic learning, okay, about this. This is how we can train the model. We can train this in a supervised setting to start with by saying, okay, we're just going to restrict how we use this model right now to supervise. So that means all of those data points that came in, those initial concepts we started with, we make sure that all of those have a labeling, right? What that now means, okay, is we can minimize the loss that we have between the starting concepts and their labels, right, based on the representations that we just came up with. Okay, so based on this, I now have this basically as like a feature vector input to just a simple classifier. Okay, we just use some neural net or something to classify. It doesn't really matter what. But what we say is that basically we want to keep reiterating over the weights and the network that we saw on the last slide. Okay, we want to iterate over using back propagation. Right, we want to iterate over these weights so that the model learns well how to classify one person from another based on those initial labels. Okay, so that's the general ethos behind the whole thing, which means that basically what you're doing there is you're saying, I want the meaning of these vectors, right, to contain information that's useful to making some classification. I'll say that once more. So we've got like a classification problem we want to solve, and we say, I want to make these features useful to solving this classification problem. And so actually what we do is we directly learn a classifier when we're building this framework at the moment. And future work will see us actually trying to move that to unsupervised. So you don't have to have a label, you don't have to directly train this network to do just one task, right, and hope that it's good at other tasks. You can actually just say, okay, I want to penalize things that look dissimilar in some way, okay, and I want to reward things that look similar. Okay? And in that way, the network will, on its own, try to learn these different groupings that will let you do whatever evil things it is you want to do on social networks or what have you, right? So I'm going to come back to this graph structure, which is the one that we started with just now and put loads of arrows all over it, right? Just to remind you what that looked like. Now, this is just a graph, okay? This isn't a knowledge graph, and this is the work that we've based our studies on at the moment, is based on just graphs rather than knowledge graphs. So how would this kind of thing look if we actually took it into a knowledge graph instead, okay? So this is the general idea that I came up with, this is just some example, okay? So you can see that it starts to look a little bit more complicated, all right? But that means that we have this extra challenge, which is to try and incorporate more information. We've already talked about how the structure of the information is important, okay, and that we can use it for the reasoning. But we can also use it to make sure that
our machines are actually taking account of not just what's nearby, but what is that thing that's nearby, and how is it related to me? Okay, all of these kind of things are something that we want to take into account. So how do we do that? Well, basically what we're going to do is at each of these points, these are all equivalent to the nodes that we saw just now. Okay, there's a direct equivalent. And what we're going to do is we're going to say, well, from this node, okay, let's look out this way. Okay, and from this node's perspective, this node here has some role that it plays, which is the fact that this owns this. Okay, that's the direction in which we're going. So we can actually then say, okay, what we want to do is we want to encode all of those different pieces of information. One is, what's this interlink between the two? One is, well, what's the type of this? Well, this is some employment that started on some particular date. So we have a date started. And we also have the actual value of that thing itself. Okay? So we want to get all of those three pieces of information, and that is what's going to build that starting vector that we saw from the off. Okay? We're going to and that's a really novel step in this domain, is to actually not just be able to take some piece of information that's consistent across the whole of the graph, right? In the sort of domains which we've started from, there might be the same vector as we kind of saw in the example I gave. Like, it's the same kind of vector just dotted around on all of the nodes of the graph. That's not what we've got here. What we've got is something which is much more richly labeled. And because it's richly labeled, we really shouldn't throw that data away. We really want to actually make sure that we make the most of that data. Okay? So that's why we're going to build that up. And this is actually quite a nice little example for me to just talk over this entity relationship attribute model that we're talking about. And this is, again, this is quite a good turning point for me to say why this is useful to you and explain something about how that works. So the general idea here is that the star that we started off with, maybe that's a company that you're looking into. Okay? So what I've done here is I've labeled the entities are the red boxes. The relationships are the cyan boxes, and the attributes are the green boxes. Okay, so what is each? Okay, so in general, you can say that an entity is something. Normally, often it's if something is physically tangible, chair, person, wall, lecture theatre, right? There's a few things that I see around here at the moment. Then you can say that in general, that's going to be an entity for each of those. Okay, what's the relationship? Well, that's often a little bit more tricky. So here we're talking about something that's maybe an action or an event or some ongoing event, as we have in this case, right, that links multiple things. Okay. Now, immediately we've actually got quite an interesting one, because if we have an employment relationship, where we say that a company is related to a person via an employment. Okay. So I don't know if that seems like an abstract concept, but that's the general, the idea here is that we can actually break a lot of things down into those kind of interrelationships. And what it allows us to do is, in a lot of other systems that you'll encounter, you'll just join a direct line from company to person and just call it employment. But the problem with using that kind of approach is when you then want to add that there's a contract on that employment, right? Then how do you add it? You suddenly got to break the structure that you had before, right, which may not be imposed. You've got to break that structure to add something else. So here we've got, well, there's also some legal construct attached to the employment, okay, and that legal construct is this contract over here, okay? So that's the crux of that. Then we have attributes. So this is the data that we're all actually more familiar with, right? At the moment, a lot of people deal with data in tables, right? And each of these columns in the table is basically an attribute of something that the table describes. Instead, we split those out. We take them out one by one, and we say, well, a person doesn't have to have a first name and a middle name and a last name, right? They might have two first names, two last names, whatever, right? So and we get this extra flexibility by instead having these attributes as just floating nodes in the graph. And we can have as many or as few, or constrain them however we want to, right? And we can have all of the different data types that you'd normally expect in sitting in those positions, right? And again, we've put in the little example about the inference here to try and just give some sort of backdrop to another example for why you might use it. So we might have, for instance, that some poor soul was employed by Grakn Labs, right? And that company was formed in 2015, right? And we might find that actually there's some information in the back of the graph that says, well, actually there's this particular law that applies to employees, right, who are part of a company that was formed 2015 or earlier, right? And so in these cases, jumping through some reasoning hoops in the background, right, in these cases, then there's this law, right, which means that there's this legal constraint on this company, which is applicable from 2014, something like this, right? These are the kind of steps that you can see that the machine's going to take. And then when this legal constraint then becomes directly connected to the company, so that when we ask for the company, we ask for all the things nearby, we see that it's operating under these certain constraints. Okay, so on the macro scale, we want to have a quick look at what does this actually look like, because I've zoomed right in just now into what it looks like on like an individual example for that individual starred case, that starting node, right? What happens in the direct vicinity of one of the nodes of interest. But what happens when we actually try and employ this across 500, 1,000, 10,000, however many items in our database we want, right? What happens then? Okay, and so here's the rough example of, so here's, no, nothing. Here we go. Here's 5 things that that we've pulled from the database, okay, that we've taken some interest in. So we've now got 6 of our starred things, right? What we're going to do is that we're going to conduct that same search for each of those starred things, right? So that same like K hops out from those starred points of interest, okay? But the important thing here is that as we do this, and as it gets more complex, and they maybe start to overlap each other, whatever, we really don't mind about that. That doesn't bother us. The important bit is what's up here in the top right corner. The important bit is that the same aggregator and combiner, these 2 processes, we have 2 sets of 2 here. We have one set that happens on the second degree away from where we started, okay, this orange step. And we have another step that happens at the first degree away from the point of interest. And the idea is that the neural nets, okay, the neural nets that we saw back here, okay, that's one of our aggregators, that we only use 2 of these aggregators in that whole system. That's the important bit here. We're not training a neural net for every concept that we encounter in the database. We're passing all of the 10,000, 1 million, however many it is that we're interested in, through the same neural net. And that's how we get all of the training data for it, right? That's how we can actually teach it something. Okay, so by passing all of that data in. But what that means is that now we've got something that's actually really lightweight when we actually come to use it. And it doesn't have to have seen something that's similar to what it's seen before in order to have an effect, right? It only needs to have seen something in the realms of what it's seen before. We only need to train, in fact, 1 weight matrices and 1 neural net layer twice, okay, once for the green ring, once for the orange ring, to get this whole system working. So there's not that much for us to actually learn in order to get the whole system up and running. And what this means is that while there's a lot of other systems where you may have to do a lot of random walking in a lot of different directions across from the thing that you're interested in, or a lot of systems right now you actually have to plot the whole of your graph and optimize over the whole graph in order to get something actually meaningful, which isn't viable if you have terabytes of data. Instead, in this case, we can just do it across a subset of however many we want, and then start using that tool on more and more data. So, what was the general idea here? The general idea, oh, well, that's gone well, isn't it? Never mind. Okay, that says KGCN at the top then. So the idea here is we're presenting a combination of learning, reasoning with a knowledge graph backend, right? That we hope is actually going to take things to the next level in AI, right? In some sort of smart, intelligent systems, okay? To try and push things forward 1 level more, okay? So we're going back to what we started with overall. And I'm going to do just a quick summary of Grakn overall and what the different components. I know it's getting hot in here, so I don't think we want to stick around for too much longer, right? So So this is what I've done this evening is I've basically touched on 2 out of 3 components in Grakn. There is a third, but we've talked about this knowledge schema. We saw that when we saw the define for the jigsaw puzzle. And we talked about knowledge schema and how we interrelate model and keep context for those models. We've talked about the automatic reasoning that we can do once we've got that. Okay, only once we've got the knowledge schema can we do this reasoning. And then we've got this extra part, which I'm not going to talk about, which is when we start doing really large scale analysis, that we want to start being able to do Pregel algorithms across our knowledge graph. Okay, so that's actually built in to Grakn so that you can just immediately ask for a number of Pregel algorithms to be performed, this is the stuff that Google's doing to index the whole of the web, right? So you can have a terabyte of information and just type a command and get the kind of information that you're asking for back, the kind of statistics that you want to see. And then overall, what you've seen multiple times through this demonstration is this, you've seen it coming, is the fact that there's this little bit in the middle called Grakn. So that is the language that you've seen, albeit we had to squint a little bit at it. So the language we're talking about here is this one, okay? I've shown you sneaky before I sort of dropped the bomb before we actually, all of this is part of Grakn, right? This is what we call Grakn. Okay, so this is this query language which is new and unique to this company, which allows you to both write this knowledge schema, write the rules that govern uncovering new facts, and also allows you to make these queries of the knowledge through the reasoner to the knowledge graph. So those are overall the components of our system, what we're up to, and hopefully this has at least stirred some thought. Hopefully it's given you an idea that maybe you can get your projects done faster using an open source database where you can query things like this. And well, now it's time for a selfie actually. That's the next thing we're going to do. But I'll take questions first. I think that's what we'll do to start with. No, that's the selfie count. No, let's do the questions first. Are there any questions from the audience? Yes, sir. If you just shout it out, I'll repeat it back to the audience. Oh, yeah.
What kind of problems did it solve? As I understand, we have to program some conditions to solve the problem, and for example, some kind of problems will be very hard to program. For example, if I want to know if in a specific picture there is a cat or not, it will be very hard to define this cat.
Okay. Should I take the mic? If we just get everyone to shout questions out, and then we'll just repeat that.
Okay, so the question here is how do you define a cat in a picture, right? That's really what it is. But in general, how do we? You are right to say that essentially the logical rules can be hard to derive. This is I don't think we should start diving into an image recognition example right here. There are real benefits to using this kind of a system in image recognition. For instance, if you want to tag up an image and you say, well, something is a vehicle, well, actually it's a plane, but you want to know it's a vehicle, you don't want to know it's got passengers, or it's a portrait, you want to know, or a picture, you want to know whether it's a portrait that has a human in it. You know, this kind of contextual understanding of what an image looks like is actually very difficult for us to represent at the moment. So the idea is that we can enrich the background data of that, and actually when we talk about it like that, the fact that a cat is a mammal, right, from this certain family, these things are actually quite easy to encode, right, and they give more context to the labeling because mammals actually tend to look similar, right, so you already start to see that you've got like more context brings the possibility that the machine can learn more. Does that answer your question? Somewhat. You'll have to come to me afterwards and we'll talk. I'll fend you off. Any more? Does everyone want to get out of this hot room? Okay. You don't. He's keeping you here, by the way. It's his fault.
So, do you understand it correctly? So, basically, first, we need to put some rules. And then the Grakn, I don't know, Grakn is the language.
Yeah.
But the algorithm will find out the rest of rules. It's like based on the rules.
Okay.
So what I wanted to do today is that I wanted to try and mix things like in together to introduce this whole thing to you. Like, why do we want to do this whole thing? So we come from it at a different angle to how we would normally come at it as a company, right? Because I wanted to try and drop the bomb later on of what we do all this for you. But what we really talk about here is we're saying first, if you're going to go step by step with how you use this system, you're going to define a schema first. Okay, so we saw schema. Let's go for schema. We saw schema under the define statement back here. This is a schema, right? So we start with define and we told it what's entities, what's attributes, what's relationships, right? Once we have this, we can write rules straight away. We can also start inserting data as soon as you've got any schema in. That schema you can actually change over time. You can add more things, you can remove things, you can restructure things as you go. And the rules, what you also asked about was the automatic generation of rules, right? That's going to be an upcoming research area. There's work already been done in that space in general. We haven't done it for our platform yet. We're actually hoping that KGCN may be able to help us with that, because once we've got these embeddings, these vector embeddings, then maybe we can use these to correlate logical possibilities for rules. So that then you can start to say, okay, well, I can look at this network graph and it happens to have in it all the people who have driving licenses, and it also has their ages. And from that, I want to be able to derive the fact that you have to be over 18 to have a driving license, right? So that's a work in progress. Does that answer all of your questions? More or less? Yeah, it's not sure. Yeah, more or less. Okay, there was another one. Not now. Okay. Not now. Just teasing you. Just teasing you. Any more?
Yeah, I can yell.
Yeah, you can yell. You can yell. Yes.
I'm not sure if you can answer that, but are there some major companies that are using your solution?
The major companies using our solution?
And what they are using it for?
No, not yet. I mean,
any smaller companies?
I haven't published the code for this yet, and when we do, it will be open source.
Okay.
So unless someone's looking at my fork very closely, then no one's seen this yet. You're actually the first people in the world to see this work. So this is up and coming stuff. We actually, most of the companies we're working with at this moment are genomics companies. And so what they tend to be interested in is drug discovery and drug repurposing. So they want to be able to classify a drug in a wider database and what does that drug look like in its current sphere? Okay. Oh, and it happens to look like this drug over here as well. Okay, so that means that maybe it also cures the same diseases as that drug over there. Does that make sense? It's the closest answer I can give you because no one's using this yet. You guys can use it, but only want to send you the link for the code. Oh, he's got a question now. He's leaving me on the floor.
Actually, the same question. I didn't get the idea of vector embeddings if you have the relationships defined. Can you give an example?
If we have, vector embeddings, if we have a relationship defined.
These relationships defined, I thought that you are using vector embeddings to define relationships.
Yes.
Between entities that you are saying that currently you are not. So why do you want and are you using
the embeddings? Okay, so I think maybe have I introduced confusion about how we actually define new relationships? Is that right? So at the moment it seems like we're creating the relationships from the embeddings. Is that right? Okay, so that wasn't the aim in this presentation to present the idea of doing that. At the moment, well, out of the box, Grakn will create new relationships for you using the rules. So those rules, at the moment you hard code them, and actually you'll be surprised with what you can do with about 5 rules in most domains. You can suddenly extract a lot more facts, including building relationships, interlinking between two things. So if I jump to a slide that's maybe relevant. Let's see, so if we go to this slide, for instance, right? So what we've got essentially here is we think that legal constraint is inferred as a relationship, yeah? Because we say that because this law exists, right, and some other like chain of events that we don't know about down here that relates to the fact that this company was formed in 2015, right? Now what we do is we've got some rule in the background that's saying when these two things occur, then legal constraint links the two, right? That's what we do. So in fact, we've got it already with the jigsaw example, right? What we did is we said that there's a relationship that exists once we find that there's a oh yeah, what code? Yeah, code. Come here. Okay. So what we did here is we said this is our syntax for a relationship, which is these normal brackets, right? With is a jigsaw piece fit. So we say, like, what we're saying with our relationship is that this is the name of the relationship itself. Okay, I know I can give it a very good name, but that's fine. And then these are the things that the relationship links out to. These are the things that play some role in the relationship. Okay, so one of those is the gap that the jigsaw piece fits into, and one of those is the jigsaw piece. Okay, but that relationship is being inferred by the rule, not by the vector embeddings. So, but included in one of the use cases for the vector embeddings is to be able to try and basically, using statistical methods, right, using machine learning methods, which this is not, using statistical methods, can we find two drugs that are interrelated, right? Does that hopefully that starts to clarify a little bit? A little bit, okay. Not doing very well here, am I, right? No one's questions are fully answered, no one's fully satisfied. Okay, anyone else want to be dissatisfied with my answer? Yes, tentatively. Oh, here we go. No, sorry. I'll shout it back to him. No. This work is in progress right now. Okay, so this is not finished. This is not. We expect that this is going to be dependent upon a lot of factors, right? Because it's about how deep in that search do you want to go? How much are you willing to spend in terms of your computational resource to go there? How many concepts do you need to look at? How dense is your graph? If you're dealing with a biomedical drug database, right, protein-protein interactions, these things are massive and really, really heavily interconnected, right? If you deal with my jigsaw example, you're probably going to get done pretty quickly, right? So it's all going to relate to that scale, how fast our queries are as a database, and then how fast we can train the network. So I don't have any speed metrics for you though. How long is this piece of string at the moment? Any more for any more dissatisfaction? Or should we take a selfie? Let's take a selfie. Let's do it. So this has become a little bit customary because you want to get involved, yeah? Oh, why you don't want to be involved? Okay. You want to be in the audience? Get in the audience. Yeah, get in the audience. Act like you were paying attention